It's the state reduction algorithm. And so, like I said, the state reduction algorithm takes some DFA M, right? And then outputs an equivalent DFA, an equivalent minimal DFA. Well, this is the claim, at least, that it will be minimal. But first of all, the DFA should be equivalent, meaning that the language accepted by M should be the same as the outputted machine, M hat. And this DFA should be minimum, in the sense that there can be no other machine M with a smaller number of states, Q hat, that also accepts the same language. Okay? So how does this algorithm work? Well, you take M, which has states, an alphabet, a transition function, an initial state, and a set of final states, and you create a machine, M hat, which has specific new characteristics for its set of states, transition function, initial state, and final state. We're assuming that the alphabet will remain unchanged. That's right, a very natural assumption, because the language you're accepting is still going to be over the same alphabet. So that's why the alphabet remains unchanged. Okay. So how does this algorithm work? Well, what you do is you start with some machine M, okay, and the first thing that you do is you're going to remove all unreachable states. So for example, if I have a machine like this, right, and I have another state like this, clearly this state is unreachable. It's unreachable in the sense that there is no string that you can read where you start at Q0 and you get to that state, right? No string permits a walk starting from Q0 to that state, right? The next thing, and this is the crux of the algorithm, is you're going to partition your set of states. So you're going to start with two initial partitions. Your first partition, S1, is going to be all of the non-accept states, right? So this step is going to be partitioning the initial partition of Q, right? So that partition is going to be all the non-accept states and all the accept states. And the idea, what you want to do is you want to keep breaking off, you want to keep partitioning these initial two sets such that you can no longer break them further. Okay, that's the idea of the algorithm. So now in step J, what you do is you want to check whether two partitions, right? You're checking if two partitions are indistinguishable, right? Well, in fact, you're checking that two states are indistinguishable. So two states are indistinguishable if every symbol that you give these two states map to the same partition, right? So if the transition function, when reading the symbol sigma starting at P, outputs some state, and the transition function starting at Q reading sigma outputs another state, then if for every symbol that you read, those two states are in the same partition, then P and Q are indistinguishable and they don't get separated, right? So imagine you have P and Q, right? So you have some other states in your partition, but you know you have P and Q. So what you're doing is you're checking for each symbol, right? When I'm in P, where do I go? And when I'm in Q, where do I go? Right? If for each symbol, I always go to the same partition, right? So let's say P1, partition 2. If these guys are always the same for each symbol, right? Then these two states are indistinguishable, okay? They're indistinguishable, and so that means that they remain in the same partition. Otherwise, so let's say if I read the symbol 0, right? So if I read the symbol 0, say here I'm at P, here I'm at Q. If I read the symbol 0, and this leads me to partition S1, and from Q, if I read the symbol 0, I go to the partition S2. If these two guys are not the same, then these are distinguishable states, and so they should go in separate partitions, right? And so then you need to do this for each pair, right? For each pair in each partition that you have so far, right? So if they are indistinguishable, they remain in the same partition, and if they aren't, then they split. Your partition splits. Okay. And so this keeps going, right? So this keeps going until you hit the step where you have created no new partitions. So if no new sets or partitions have been created from the step j minus I to the step j, you finish, right? Your algorithm stops. And then your output, right? Your output, remember, is a machine. That's a DFA, okay? And so your machine M hat, each partition, right? Each set S, or really these are partitions. So each partition will become a state Q hat. The initial state of your machine M hat will be the partition that contains the initial state Q0 here, okay? And then finally, the set of final states will be the set of partitions that contain at least one final state from the original machine, right? So if you have, let's say, two partitions, P1 and P2, if you have like Q3 and Q6, and Q6 belong to F and Q3 belong to F, then P1 and P2 will belong to F hat. Okay. And then this machine M hat will be the minimal DFA. And so what I omit here is I omit a correctness proof. So I omit proof of correctness. But there is an exercise that asks you for a specific machine to prove that it's minimal. And that same proof technique can be used in general to prove the correctness of this algorithm. Okay, so I know I've been talking a lot. Let's actually look at an example to see how this truly works. Right, so I have this machine M here. It accepts some language. I don't really care what the language is, but I want to reduce it, right? So what do? Well, I take M, I feed it into my state reduction algorithm. What's the first step? The first step is to get rid of all unreachable states. So what are the unreachable states? Well, if I'm Q0, I can reach Q1, so that's fine. I can reach Q2, I can reach Q4, I can reach Q3, but there's no way for me to reach Q5, right? Because from Q0, there isn't any incoming edge to Q5. So then Q5 immediately I can remove, right? And so that's what I do here. The state here is just taken out, right? And then I start my actual partitioning, right? So remember, what's the very first partition? The very first partition is Q minus F and F. So in this case, Q is Q0, Q1, Q2, Q3, Q4, and F is Q2, Q4. Right, so then S1 is assigned Q minus F, which is Q0, Q1, Q3. And then S2 is assigned Q2, Q4, right, which is F. Okay? So those are my first two partitions. Now what I need to do is I need to do this indistinguishable thing, right? So how do I do this? All right, let's do it here actually. So I have Q2, Q4. All right, so this is the first iteration. In the second iteration, I need to check each pair of states, and I need to check whether or not they're distinguishable, right? So let's start with Q2 and Q4, right? So the first thing I'm going to ask is, are Q2 and Q4 indistinguishable, right? This ind is short for indistinguishable. Well, let's see. So if I'm in Q2 and I read a 0, then I go to Q4. So I end up, right? So if I'm in Q2 and I read a 0, I go to, so if this is S1 and this is S2, I go to S2. If I'm in Q2 and I read a 1, I go to S2. Right, so let's see if it's the same thing for Q4. Right, so for Q4, if I read a 1, so if I'm in Q4, I read a 1, I go to Q2. But Q2 belongs to S2, right? So again, I go to S2. And then for Q4, if I read a 0, then I'm in Q4, I read a 0, I go to Q2. But Q2 belongs to S2, so again, I go to partition S2. So then I need to check for each symbol, is the partition, right? So the partition of this guy equal to the partition of, of this guy, right? So that's the question. Well, in this case, yes, right? So I shouldn't have crossed them, but if I read a 0 from Q2 and Q4, I go to the partition S2. And if I read a 1 from Q2 or Q4, I go to the same partition S2, right? Notice that, and there's one thing that you have to be careful here. If it had been, let's say, if it had been that, so from Q2 and Q4, I went to S2, and then from Q2 to Q4, when reading a 1, I went to S1, then that's still okay, right? Because for zeros, I go to S2. For ones, I go to S1. What's not okay is if I cross for a given symbol, right? So if I had S1 here and then S2 here, then that's no good, right? That would have been no good, and I would have had to split my partition, okay? All right, and so then I just redo the same exercise for every pair. And the one trick for you to make this go faster is you can never add states to partitions, right? So you don't need to cross-check Q0 with Q4, right? You already know that they're distinguishable, right? Because Q0 is one partition, Q4 is another partition. They're not going to merge, right? The only thing that can happen is these partitions can split, right? These guys can split, and these guys can split. I know that this is not going to split, so now all I need to check is this going to split, right? So that's what I'm going to check. So this was my initialization state. So this was step 1. This is step 2. Step 2, I've already done this. Now what I need to do is I need to check, let's say Q0 and Q1. Are they distinguishable or indistinguishable? So Q0 and Q1. If you read a 0, if you read a 0. And notice that at step 2, what I'm doing is I'm checking the partitions from the previous step. So S1 and S2. Okay. So at Q0 and at Q1, if I read a 0, so for Q0, I go to Q1, which is part of S1, Right, so that's part of S1. But from Q1, if I read a 0, I go to Q2, which is part of S2. Right, so that's part of S2. So already, these two states are distinguishable. They're distinguishable. Okay? And so I know that I can split this partition already. So now the only thing I need to check is Q3 indistinguishable from either Q1 or Q0, right? So I can do that quite quickly, by just looking at my transition graph. I'm not going to redo this process. So if I'm in Q3 and I read a 0, then I go to the partition S2, but from Q0, I go to the partition S1, right? So already I know that Q0 and Q3 are indistinguishable. How about Q1 and Q3, right? So Q1, when I read a 0, I go to the partition S1, right? Because I go to Q2, which is part of the partition S2. Well, actually, let me write this one down. Okay, so for Q1 and Q3, if I read a 0, I go to the partition S2. And if I read a 0 from Q3, I go to the partition S2. So far, these guys are the same. What happens if I read a 1? If I read a 1 from Q1, so if I read a 1, so this is either 0 or 1. So if I read a 1 from Q1, I go to Q4. So I go to Q4, which is part of partition S2. However, if I'm in Q3 and I read a 1, I go back to Q1, right? But Q1 from the previous step is part of partition S1. So it's part of partition S1. So these guys are different, right? So that means that Q1 and Q3 are distinguishable. So each pair of states here is distinguishable. And so they go in separate partitions. And if you redo this exercise, I won't, but if you redo this exercise, you'll see that Q2 and Q4 never split, right? They're never distinguished. And, Q0, Q1, Q3, you don't need to bother rechecking because you can't remerge these states. And so now what I do is I just assign these guys to states, right? So I assign these guys to states. So I have the set Q0 as a state, the set Q1 as a state. Oh, okay, I haven't done that yet here. Okay, sorry. So I'm going to do that in the previous slide. So the states have been identified. So now I do this in the next slide. So I have the set Q0, the set Q1, set Q3, and the set Q2, Q4, right? And so then the transitions, so you might be asking yourself, so what are the transitions? Well, I look back at my machine M, and because I've reduced, because I can't reduce my states further, I know that any state in this partition, if I read, let's say, 0, it's going to go to the same exact partition, right? So all the states in this partition, if I read a 0, they're going to go to this state, right? Otherwise, my algorithm wouldn't have stopped, right? And so I read the transition from M, and I apply them to my partitions, and I get this machine. Okay, so that's the state reduction algorithm, and this is an example of how to use it. So I'll also show how to start from scratch and how to sort of reduce a machine manually. So if this hadn't been done, if you hadn't seen these slides, could you have done this yourself? Okay, so that'll be probably the next video.